In this video, we're going to look at taking the derivative of an exponential function where that base number is e. I know that's a silly thing to hear, but e is a number in mathematics. If you look at the formula at the very top, when you take the derivative of an exponential function where e is your base, you're going to make an exact copy of what you see times the derivative of the exponent. And that's the reason that notation has an e to the u in the bracket, is when you take the derivative to the right side of that formula, you'll see e to the u. That just represents making an exact copy. And then the du over dx, that just says take the derivative of whatever the exponent is. Moving into our first example, y equals e to the 2x cubed. When we take the derivative, we're going to make an exact copy of what we see. So that's e to the 2x cubed. And then we're going to focus on just the power. 2x cubed, what is its derivative? 6x squared. And it's very quick to take a derivative of an exponential function where the base is e. Make a copy times the derivative of the power. In the second example, we have y equals e to the x squared minus x. So our derivative is going to be exact copy times the derivative of your exponent. What's the derivative of x squared minus x? Very good. 2x minus 1. I'm going to put that in parentheses because it's very easy to leave that off. You're not required to simplify anymore. If you wanted to, you could also write this as 2x minus 1 out front times e to the x squared minus x. And just like that on the example above, you can, but you're not required. You can write that derivative out front. It's just however you want to write it, whichever way you prefer it to look. Either way is fine. The demand function is given by p equals 73, e to the negative 0.40 and 75x, where p is in dollars and x is in units. Part A of this problem, and this will match what your homework assignment has in it, what price yields maximum revenue? We're given a demand function, P. Revenue is X times P. And so that's going to be X times 73 e to the negative 0.4025x. Okay, so that's going to give us R equals 73x e to the negative, and I'm not going to read out that decimal, it's just too long. Okay. Now if we think of these as an algebraic times an exponential, when we take the derivative, because if we're going to find a maximum revenue, we need to know where r prime is equal to 0. We can take this derivative successfully using product rule. Derivative of the first term times the second plus the first term times the derivative of the second derivative of the power is negative, we'll put that in parentheses, 0. Just that value. Okay. Now, if you look at both of these terms carefully, they both have 73 and that exponential e part in common. So when we're going to find our critical number, we set the derivative equal to 0. I'm going to factor out the part they have in common, and I'll tell you in just a second why that will help you a lot in your problem. And if we factor that out, the first term is exactly what we factor out, so it has a 1 left over. The second term will have an x left over and that decimal from the farthest set of parentheses. And then don't forget that little x there. Okay, now that's quite a bit of factoring, and that's not always easy to look at. But if you were to redistribute the outside term back through the bracket, you would get those two terms right above. Verify with yourself that that is true. Okay, now the reason I decided to factor that out is because let's say you were to graph that part of it, or if you remember back from college algebra, the graphs of exponential functions, sometimes they don't cross the x-axis, and that's exactly the case with this one. Turns out this term is never 0. We get to ignore it. It will not have a critical number. In the bracket, if we put this equal to 0, because you set each factor equal to 0, but that leading one's never 0, that's why we get to ignore it. This one, if you were to solve for x, you would get 40,000 units. Now that's not what this problem part A is asking. Let me go up here and actually label this part A, because there is a part B, and I'll have to do it on the next slide. I'm running out of real estate. But part A asks what price in dollars rounded to the nearest cent will yield a maximum revenue. Go back to your price function and plug in 40,000. This will be the price of producing 40,000 units. So that is 73 E, and then we've got that long decimal number. But where the X is, plug in 40 grand. To the nearest cent, I've got $26.86. Continuing from the last problem, part B, what is the max revenue at the price found in part A? Well, remember when we first built our revenue function, revenue is number of units times the price at which they're sold. Well, we know that now. 40,000 units were produced in order to maximize revenue, and the cost we found was $26.86. Let's see, let me write that a little bit smaller. And if you multiply these, we will get a revenue of, and on part B in your homework, you're asked to round to the nearest dollar. I've got $1,074,208. The balance A in dollars in a savings account is given by the formula A equals 5,000 times e to the 0.07t, where A is the amount in dollars, T is the number of years the account is active. Find the rate of change in the balance when T equals 10 years. Rate of change is derivative. So let's find the rate of change at any given time t. In the previous example, when we created revenue, we had to multiply x times the demand function, and that gave us a 73x e to that long negative decimal value. Both parts had a variable. In this one, we catch a break. The 5,000 does not have a variable attached, so we don't have to use product rule. We can treat 5,000 just as a constant. So remember, with E, you make an exact copy of what you see, times the derivative of the exponent. So if we multiply 5,000 by 0.07, I get 350. So the account changes. Now this is for the rate of change for any number of years that the account is active. 5,000 times 0.07 is 350. We were specifically asked to find the rate of change at the 10-year mark. So we're going to plug a 10 into that variable t, and that's 350 e to the 0.07 times 10, and we're going to round it to the nearest cent. 350 e to the 0.07 times 10. I get $704.81. That's the growth rate of the account balance at the 10-year mark. It's growing at that many dollars per year. The longer the account is active, the larger that value would get. But at the 10-year mark, that's how fast the rate of change in the balance is occurring. When you take the derivative of a natural log function, derivative of ln u, you flip or take the reciprocal of whatever trails the natural log part of it, and then you take the derivative of whatever trails. So it's 1 over u times the derivative of u. For our first example, 4 minus x squared is in that u position. When we do a derivative, take the derivative, we're going to do 1 over, and for this problem it's 4 minus x squared, times the derivative of 4 minus x squared, which is negative 2x, and it's just that fast. It's the reciprocal times the derivative. If you wanted to put this all in one fraction, please feel free to do so. It looks a little neater. It's not required, but it just looks better. And so that's what I would enter for a derivative, negative 2x over 4 minus x squared. It's just personal preference. For our second derivative, or second example, not second derivative, 1 over 3x times the derivative of 3x. Now I put this little one in here because sometimes you can have a reduction, like these 3's cancel, and if there's a reduction there, make it. If there's not, don't force it. Not every one of them's going to have a derivative over original that simplifies. And our first example was proof of that. There are times where your logarithm is not a natural logarithm. A natural logarithm is a log base e. But if your base number is something other than e, and I've got an a written for the base number, then it adds one component. You're still going to do reciprocal of u times the derivative of u, but you also have to include 1 over natural log of the base that's given in your problem. The first example, we have log base 7, of x, that little x at the back, consider that your u. Just line it up with the derivative formula right above. When we take the derivative, we're going to have 1 over u. For our example, it's 1 over x times 1 over natural log of the base number, that's natural log 7, times the derivative of x, which is just a 1. So just be careful to follow that recipe above very carefully. If you want to put it all together, it'll just look better. It's actually not required. But that's how it would look if you put it all together. Okay, our next example, a little more involved. Okay, so we have reciprocal first, if you follow the recipe at the very top. So that's 1 over 3x cubed minus 7x squared times 1 over natural log of whatever number is your base. In this problem, it's 3, times the derivative, which is 9x squared minus 14x that's plenty good. If we wanted to combine it, where it just looks better if you combine it. So we're going to have 3x cubed minus 7x squared times natural log of 3. Let me make that look better. Natural log of 3. And then that derivative at the far end above, we're just going to write that as our numerator. And so it's just a matter of following that recipe. I don't expect you guys to memorize that. It's not used a whole lot, but I wanted you to see a few examples because you'll run across a few in your homework.